Okay, so in this lecture, we will discuss common source amplifier. So we will use the MOSFET to start designing amplifier. But before that, we need to establish the small signal model of the MOSFET, just like we had did for BJT. Okay, so let's first discuss the small signal model of a MOSFET. Okay. So, if we remember, okay, the BJT, we know that in BJT, let's try to compare the same thing with the BJT, because then it will be easier because now you are very familiar with the BJT. So, it's better to compare the two, and because they are very quite similar, very close. Only slight difference is there between the MOSFET and the BJT. So in this case, I had my collector, emitter, and base. So these were the three terminals of the BJT, and this is my BJT. Okay, and what we had seen that this one, I have my R pi, and I have my current dependent current source, IC equal to beta times IB. Okay, this is what we had seen. Okay, this is my collector, this is my base, and this is my emitter. So this is the small signal model of the BJT. We would like to try and get similar kind of small signal model for the MOSFET. So in fact, there will also be a current source in case of the MOSFET, and only there will be a slight difference here because this R pi will not be there in the MOSFET because we know that from the gate to the source, the impedance is infinite. Okay, so again, let's draw it, and then things will be more clear. Okay, so this is my MOSFET, and this is my drain, this is my source, and this is my gate. Okay, so we will try to get a similar kind of model like this. Okay, and of course this model, when we were talking about the BJT, we were talking about in the region where the active region, right? This region of operation in case of the BJT. Okay, and this model is valid only in this region and not in the saturation region. Similarly, in case of the MOSFET, whenever we are trying to do the small signal analysis, this is valid in case of this region, right? Same, and in this case, of course, the MOS is called the saturation region. Okay, saturation region of the MOSFET, right? So this ID and this is VCE. Okay, so yeah, so this has to be very clear. It is in the saturation region. Okay, so now assuming that the MOSFET is in the saturation region, my ID is equal to half mu n C ox W by L VGS minus VTH whole square. Again for the NMOS. Okay, so we'll first try to see the small signal model of the NMOS, and once you understand all the circuits and the small signal model of the NMOS, understanding PMOS is very easy. Okay, so now, so here basically what we try to do is I try to find out the relation how my this small IC is changing with these small IB. So that was what that's how it happened here. So here, of course, my this there will be a small change in the ID. Okay, so which is basically this delta ID. So I want to know in relationship with the change in the VGS. Okay, because this VGS is a parameter here, input parameter. So what I will do is dID by dVGS. Okay, so basically it means that it is half, this 2 will come here, 2 will come here, and it will get cancelled with this 2. Of course, mu n C ox W by L is a constant. Okay, and then it becomes VGS minus VTH. Okay, so basically yeah, so basically this is change in the ID, which is nothing but this small ID by small VGS is equal to mu n C aux W by L VGS minus VTH at a particular DC operating point. So across these, how my ID is varying with change in the VGS, and this term is called the GM or the transconductance. The GM is called the transconductance. Why this is called so transconductance? Because if you see here, this unit here is current by voltage. Okay, so that means it's the inverse of the resistance, which is conductance, right? Current by voltage is the conductance. But if you see here, the VGS is the change in the gate and the source, right? The small VGS is between here, right? Between the gate and the source. The voltage is varying between the gate and the source, but whereas the current is changing from the drain or the source, so it is not from the same terminal. When we talk about the conductance, right, of a resistance maybe, so we are discussing about the current and the voltage change across the two terminals, across the same terminal. Okay, but here, because we are discussing about the current in one terminal, whereas the voltage applied is on the terminal. That's why this additional term comes, which is the trans comes. Okay, so that's why this transconductance comes. Okay, and of course here we can do some manipulation, and we can get the different formulas of the GM. Okay, so what I can do is if I just do some simple mathematics, just try to replace this whole term VGS minus VTH with this one from equation number 1, I can express this whole thing in terms of ID as well. So it will become square root of, right? Because I need to take square root here. 2 will go here, and then this will come down. And if I do the multiplication, so what I'll get is 2 mu n C aux W by L ID. So I can write ZM in terms of, in terms of the ID or VGS minus VTH. So basically what it means is that we are doing a differentiation at one point, and we want to see how much is the change in the ID with the VGS, just like we did for the, I should say that for the BJT as well we did, and we try to estimate the R pi, which is the slope. So GM in this case, it's also a slope only. So because we know that this is the relation so this is my curve is going to look like if I plot this ID with respect to the change in the VGS. So basically we are selecting a point here. We are selecting a point and trying to find out the slope. Okay, slope at this point. Okay, so basically at a particular ID, I'm trying to find out this slope. Okay, basically there will be a change in the small VGS, and there will be a change in the ID. Okay, so yeah, so there will be a change in the ID there along with the change in the VGS. So this slope is the GM. Okay, GM is basically the delta ID by delta VGS. Okay, so change in the ID by change in the VGS. Okay, this is the GM. Okay, so now with this we can come with the small signal model. Okay, of the we can derive the small signal model of the MOSFET. So the small signal model of the MOSFET is going to look something like this. So I have my so this ID is a current source, this ID, and it is changing. If you see here, ID is GM times VGS. Okay, GM times VGS. Okay, and of course this is my source, this is my gate, and this is my VGS voltage. As we know that there is no current flowing from the gate to the source in case of the MOSFET, it's an insulator, right? And the current flowing from the drain is ID equal to Gm VGS, and there is no relationship between the gate and the drain. Of course, here we have to make sure that the transistor is in the saturation region, that the the condition is that my VDS should be always greater than VGS minus VTH. Okay, so this is the condition that we need to follow, that the NMOS is in saturation. Okay, NMOS is in saturation. This is the first condition. In the linear region, this may not be valid. This small signal model is not valid. So this is the small signal model of the MOSFET, and you can see that it is very similar, right? It is very similar to the one that we have. Okay, so in fact, you can also write in this case the relationship between the current. We can express this current as in terms of the VVE voltage, right? So VVE voltage. So then also it is possible, right? Then the small signal model becomes quite similar. Only in this case we have this R pi, the resistance, because there is a conduction between the base and the emitter. But in the MOSFET we don't have this current conduction, but only the voltage difference, and this voltage difference VGS can be written, or the ID can be written as Gm times into this voltage difference VGS. Okay, so this is the small signal model of the MOSFET. Okay, so with this, let's try to design a let's try to design a common source amplifier. The common source amplifier is analogous to the common emitter amplifier that we have been discussing a lot. Okay, so again here also I'll have a biasing resistor, RG1 and RG2, and it will be connected to this gate of the MOSFET. Okay, and I have my resistance RD. Okay, and of course my V out is from here. Okay, and I'll be applying a signal at the gate through a capacitor. So all the things remains almost the same. So there will be a slight variation in the expression of the gain, but the majority of the stuff remains the same. Okay, so but there is some advantages that we have in the MOSFET. Okay, the advantages is that there is no current flowing inside this gate, right? So in this gate there is no current flowing. Okay, so whereas in case of the BJT, there's a current flowing inside the gate. There was a current flowing inside the gate, but in case of the MOSFET, there is no current flowing, so it becomes very easy, okay, to solve the MOSFET problems. Okay, so I have my drain, I have my source, I have my gate. So what we can write is this gate voltage VZ. We can directly write. We don't have to even use the Thevenin's theorem because there is no current flowing inside. So it just becomes the VZ becomes RG2 into VDD by RG1 plus RG2. That's it. Done. Okay. And of course, we can find out the DC current ID. Okay. This is RD, of course, as ID equal to half mu n C ox W by L VGS minus VTH. Okay, whole square. Okay, we can write it as VGS because source is grounded. Okay, so of course again we have to see that this condition is this is in saturation region. That means the VDS should be greater than VGS minus VTH. So this we need to see, right? And if it is satisfied, then it will be in saturation region. And if I am using it as an amplifier, it has to be in the saturation region. We'll come to this one more in details later, especially when we'll discuss about the voltage swing. So I need to make sure that this MOSFET is a saturation region. Otherwise, I will not be able to use it as an amplifier. Okay, so it will not be behaving like an amplifier. Okay, if it is in the linear region of operation. Okay, so now let's try to draw the small signal model of this one and try to estimate what is the gain. So this is the simple basic DC analysis. Okay, so once I have found out what is my ID, from that ID I can easily estimate my ZM. Okay, and the corresponding small signal model can be done. So to do the small signal model, just first draw the small signal model of the MOSFET first. Okay, so this is my ZM VGS. The ID is equal to ZM VGS, current flowing, and of course this is positive, this is negative. Okay, VGS. So we need to always first draw the small signal model of the MOSFET first, then do the necessary connections with all the resistance. Source in this case it is grounded, so no issue. Okay, the drain is connected to the resistance RD, and of course the Vout is we are tapping the Vout from here. Again, I'm going this one little fast because I know you are very familiar with these stuffs when we were discussing about all these things in the for the VJT, right? So this is quite similar, and of course the RG1 and RG2 comes in parallel here. Okay, comes in parallel here. This is RG1 parallel RG2. Okay, and of course I have like my signal here. This is my V in. Okay, and yeah, that's it. So this is my small signal model, and my current ID is flowing through this. Okay, ID. Okay, there's no current flowing from the source to the get to the source. Okay, and of course this is my drain. Okay. So let's try to write down the expression of the Vout. Again, the solution, the way to solve is same as what we have done from the C amplifier. So first we will write this Vout. Vout is again minus ID into RD, because the current is flowing in this direction from the ground to Vout, so the minus sign will come. Okay, and what is ID? ID is nothing but minus ZM VGS into RD, and in this case VGS is equal to V in, because the RG will not come into picture because it's directly applied here. So until unless we don't have an RS here, so this RG1 RG2 is not going to come into picture. So my ZM V in RD, so since V in equal to VGS. Okay, so therefore my gain V out by V in is equal to minus ZM RD. Okay, so yeah, so this is the expression of the gain that we get from the common source amplifier. Okay, so yeah, this is quite similar. Actually, this is quite similar. In case of the common emitter, we have got this again as RD RC by VT. Okay, so sometimes in case of the BJT, this term is called, this term is also called as the ZM, right? It's also called as the ZM. Okay, so that's why it's quite similar. And in fact, if we call this as a GM, you will see that I can also model my BJT something like this: R pi VBE if you see here, so this is coming out to be beta times IB. Okay, so this IB I can write it as, I can write it always, IB I can always write it as BBE by R pi. Okay, so because this is positive and negative BBE, and if you see this BBE and beta by R pi, it is nothing but, it is nothing but IC by PT. So this I can write it as ZMBBE. Okay, so this model becomes exactly quite similar to the MOSFET. Of course, only this R pi is there, but it can also express as ZMBBE. So if you see in that way, the gain is the gain expression of the gain is quite same as the expression of the gain of this common source amplifier is same as the common emitter. Okay, so of course you should not get confused, but what I want to show you that it's not different. Okay, it's not different, although the expressions may be little here and there may be different, but the philosophy remains the same. So if you know how to solve the circuits of the BJT, solving circuits of MOSFET is very similar, but of course you need to do some practice to get used to the terminology of the MOSFETs. Okay, so yeah, so this is my common source amplifier. So okay, so now we want to know what happens to the voltage swing. Okay, so in case of the common emitter, the voltage swing was from VDD to 0.3, but in this case it is little slightly different. Okay, so let's see that. So CS stands for the common source. Okay, so maybe let's write it here, common source amplifier, CS amplifier. Okay, so when we discuss about the BJT, the voltage swing was allowed to go from VDD to 0.3, because we know that after 0.3 only the BJT was going into the saturation region from the active region. But in this case, if the we don't want the MOSFET to go into the linear region. Okay, so the linear region is the analogous to the saturation region of the BJT. Okay, we should not get confused with the terms. So yeah, so little practice is required. So in this case, the highest one it will go to VDD, and the lowest one it will go to VGS minus VTH. Okay, because if it is lower than this, if this voltage comes lower than this VGS minus VTH, then the transistor or the MOSFET NMOS is going to go in the linear region. So to make sure that the MOSFET is always in the saturation region, we have to make sure that this output swing never goes below VGS minus VTH. So this is the lower limit for the voltage swing. Okay, so this is the voltage swing of the common source amplifier. Okay. Okay, so now let's try to see what's the gain of the common source amplifier with a source resistance. Okay, CS amplifier with source resistance. So I need to add a resistance here. Okay, RS, and we'll see what it is, the expression of the gain. Okay, so let's try to draw the small signal model of this one and try to find out the expression of the gain. So again, for a small signal model also, we can just copy this entire thing and just put a resistance here. So I have copy and pasted it. So you just need to add a resistance at the source. So now we need to find out the gain. Okay, so now if you see here again, we can start with the expression that my V out is equal to minus ID into RD. This is common because ultimately this is not coming to picture, so I'm just trying to find out. And then this I can write it as, again I can write it as minus GM VGS into RD. Okay, so now what is my VGS? If you see here, if you see the VGS is basically, because now the source is not grounded, a current is flowing through this, right? So the VGS will be basically, let's try to write the KVL in this loop. Okay, so at this point I have my V in. So if you see here, so let's call this as equation number 1. Okay, so if I write the KVL in this loop, what I will get is V in minus the potential drop is the VGS minus the drop across this one is, because the ID current is flowing through this, same ID current is flowing through this, right? The same current ID is flowing through this, so it will be minus ID into RS is equal to 0. Okay. Okay. So now what I can write is I can do some simple this one again. My V in minus VGS minus ID, we know that this is GM into VGS into RS equal to 0, implies I can get my VGS is equal to, right, VGS is equal to, I can take out this side and take common, so 1 plus GM into RS. Okay, so this is my equation number 2. Okay, so substituting BGS from equation number 2 to equation number 1, we get, so from 1 and 2, okay, so my V out is equal to minus GMRD. If I substitute this one with a VGS, it is V in 1 plus GMRS. Okay, so therefore my gain is V out by V in. Okay, so if I just bring the V out, V in this side, I'll get minus GMRD by 1 plus GMRS. Again, this expression is quite similar to whatever we had seen in the BJT case, and as we know that when this gain AV is approximately equal to RD by RS minus RD by RS, the ratio of the two resistance, when this term, right, GMRS is much greater than 1. Okay, so this also we had seen, like in case of the BJT also. So we were getting some kind of similar term, and when we did the approximation, we got that that the gain is equal to minus RC by RE. So here also we are getting the ratio of the these two resistance is the gain of this amplifier. Okay, so this is the common source amplifier with a source degeneration, that if my GM into RS is very large or much greater than 1, the gain is coming out to be minus RD by RS. And of course the same philosophy also applies here, that if I connect the capacitor, right, if I connect a capacitor CS, then I can restore my gain back. And of course it also has it also has the just like we had seen that in case of the common emitter, when we had the resistance here, the variation of the gain with change in the beta was less. So similarly here in this case, with change in the ZM would be less if I connect this resistance RS. But then to restore the gain back, we can connect this capacitor at the source. Okay, so again the same thing is repeated, but only there's a slight difference in the expression notations, right? But the philosophy behind the BJT and the MOSFET is same. Okay. Thank you. So with this, we will end our discussion on the common source amplifier. Thank you.